Yo, physics with Let's look at how polar coordinates help us in the chapter of magnetic effect of current. So for example, we will consider an infinite line wire. Let's consider an infinite line wire. And let's say that line wire is along the z-axis. So let me mark it by yellow. So this is my line wire. Let's say the current is I. This is my xy plane. So z-axis is outwards, pointing towards us, perpendicular to the plane of the screen, and the current is flowing along that line wire. Right. So the field at a distance r, I know the magnitude of the field is mu naught I divided by 2 pi r. And how will the field lines look like? The field lines will look like circles in the anti-clockwise sense using the right hand rule. Alright, so this is like the field line at a distance r. So can I express this magnetic field in vector form in polar coordinates? So first of all, let's define polar coordinates in the xy plane. So at a distance r, I define two unit vectors, one pointing along r, which is known as r cap, and the other unit vector is perpendicular to r cap in the anti-clockwise sense. Let me actually call it phi cap. Alright, so if I travel perpendicular to r vector, then that unit vector is called phi cap. Okay, so in this particular situation of the infinite line wire, can you see that the magnetic field is only along the tangential direction to the circle, so it's only along phi cap. So I can write it as phi cap. This is the vector form in polar coordinates of the magnetic field of an infinite line wire. Now why is this useful? This is very useful when you want to calculate the line integral of the magnetic field. So let's do that on the next page. So suppose I want to calculate, I have a current along the z-axis and I want to calculate integral b dot dl along some curve. So this curve starts from this point, let's call it point 1, and ends at point 2, and I want to calculate the line integral. So let's say this angle is some phi 1 with the positive x-axis, and this angle that position 2 is making with the positive x-axis, let's call it phi 2. Alright. So I want to calculate integral b dot dl. So first of all, how do we write dl vector in polar coordinates? Let's take a look at that. At some distance r, if I travel in some direction by a distance dl, we'll call that displacement dl vector. Can we write its components? One along r, so we can say that is dr, and that will be along r cap, and one perpendicular to r. So these are the two rectangular components. And if you notice, if I travel perpendicular to r by an infinitesimal amount, so let's say that the position vector will rotate by some angle d phi. So this, let me draw a blue line here. This blue line can be represented or can be approximated as an infinitesimal arc of a circle of radius r, and therefore this blue line will have a length of r d phi, and therefore my dl vector, in general my dl vector can be broken down. My dl vector is this way. It can be broken down into two components, one dr r cap and the other r d phi, and that's in the direction of phi cap. So in general I can write my dl vector as dr r cap plus r d phi cap. Alright, this angle is phi and this position vector has a magnitude r. So we know how to write the magnetic field of an infinite line wire in polar coordinates as mu naught I by 2 pi r phi cap, and we know dl vector also in terms of polar coordinates. Now all we have to do is take the dot product to evaluate this integral. So let's do that on the next page. So now it's very straightforward. I know my magnetic field is mu naught I divided by 2 pi r phi cap, and I know my dl vector is dr r cap plus r d phi cap, and therefore b dot dl is going to be, the dot product will only involve the phi cap terms, right? Because phi cap and r cap are perpendicular to each other, their dot product will be 0. So I'll have mu naught I divided by 2 pi r into r d phi. The dot product of these two unit vectors will become 1. Alright, so can you see that r gets cancelled out? And that is the crucial point here, because this leaves us with only d phi. And thus, this integral is independent of the distance of the points. The points 1 and 2, it's independent of the distance. The only thing that matters is the angle that points 1 and 2, the position vector of 1 and 2 are making with the positive x-axis. Alright, so it doesn't matter how you travel, it doesn't matter the distance of 1 and 2, only thing that matters is phi 1 and phi 2, because once I integrate from 1 to 2, I'm basically integrating from phi 1 to phi 2. So I'll have mu naught I divided by 2 pi to phi 2 minus phi 1. And these angles are supposed to be taken in the same sense like you do in trigonometry, from the measured in the anti-clockwise sense from the positive x-axis. Alright, so this is the integral of b dot dl. So if they ask you any line integral from any point to any point, you should be able to see that you can just use this formula directly. If you want, you can remember it, or if you can remember the expressions for the magnetic field and the dl vector in terms of polar coordinates, then you can arrive at this expression very quickly even in the exam. Alright. Let's also look at the familiar result that if I have a closed loop, Ampere's law closed loop, and I have a current I, then integral b dot dl, and this circle represents the integral over the closed loop, should be mu naught I. I know that. Does this also come from the result that we just got? Yes, it does, because if I look at, this is point 1, and I start traveling, and I start integrating. Remember, we have to measure the angles with respect to the positive x-axis. So first angle is 0, and the second angle, as you travel and you come back here, that angle will be 2 pi. Right? So I'll have integral b dot dl would be mu naught I divided by 2 pi into phi 2 is 2 pi, phi 1 is 0. And this is exactly what we know from Ampere's law. Alright, if you travel the loop twice, for example, you can even consider an Ampere's loop that encircles the current twice. For example, or what I mean by this is, like, you travel here, this is your Ampere's loop, you're traveling, and then you again travel this way, and you come back. Alright, so you've encircled the current twice. You've gone this way, then this way, and you come back here. Okay, so in this situation, if I ask you what is the integral b dot dl, what would the answer be? That would be mu naught I divided by 2 pi. You've encircled it twice, so the final angle that you arrive at is 4 pi minus 0, 2 mu naught I. This will be the answer. Okay. So there was a question in JEE Advanced 2024 that could be solved very, very easily using the concept that we've just studied. So the question went like this, that you had a current along the z-axis, like we do, a long wire, and the question asked us to find the integral of magnetic field from, let's call it, point 1 and point 2, and the coordinates of point 1 were minus root 3a, comma a, comma 0, where a is some constant, positive number, and point 2 coordinates was a, comma 0. Alright, this is x-axis, this is y-axis. Alright, so point 1 will be in this second quadrant. The question asked b dot dl from 1 to 2. That's it, that's all the question asked. And it's pretty easy to do it now using the concepts that we've studied, because all we have to do is measure the angle. So this is phi 1 and this is phi 2, right? And actually I don't remember if the question asked 2 to 1 or 1 to 2, but if the question asks 1 to 2, then you should be able to see that this integral will be negative. How much will that angle be? So basically we only need, what do we need? Mu naught I divided by 2 pi into phi 2 minus phi 1, right? So we only need the angle between them, correct? That is the difference between the angles. So what will the angle between them be? That's pretty straightforward from just geometry. This is A, this is root 3A, so of course this is 30 degree, so this is 60 degree. And on the other side, this is obviously 45 degree with the coordinates A comma A, right? So therefore my phi 2 minus phi 1 would actually be negative in this question that I have given, but if I recollect correctly, in JEE Advanced they had asked the integral from 2 to 1. Alright, so you'll have phi 1 minus phi 2. Okay, just make sure that you select this correctly. So the order correctly. Alright, so in this particular, in the question from JEE Advanced, if I remember correctly, it was phi 1 minus phi 2. So you'll have a positive answer. And phi 1 minus phi 2 will be basically 60 plus 45. Right, so pi by 3 plus pi by 4. This will be 7 pi by 12. And therefore this will become mu naught 7 mu naught I divided by 24, and that was the answer. So it's a pretty straightforward problem, but most students found it very difficult because they were trying to actually integrate in Cartesian coordinates, and that would obviously be very long. Okay, all right. Let's also take a look at another application of this polar coordinates. In the same situation where I have a line wire along the z-axis and I have x-axis and y-axis here. And let's say I want to find the force on a current carrying segment in the xy plane. So my current in the line wire is along the z-axis, but I have another current carrying wire or segment rather, any curve rather. Let's say 1 to 2, which is carrying, let's say, current some I dash. And I want to find the force on this red segment. Okay, so what is the force? Can I write my force on a current carrying segment as I dash into dl vector cross b vector, right? So b is produced by the infinite line wire and dl vector is along the segment from 1 to 2. Now once again I can write dl vector as I can write it as dr r cap plus r d phi cap, whereas my b vector produced by the infinite line wire is mu naught I divided by 2 pi r phi cap. Now I have to take the cross product. So first of all, cross product of phi cap and phi cap will be 0 because they are parallel. So we are only left with r cap cross phi cap. Now in which direction will r cap cross phi cap be? I have r vector this way, so r cap is this way and phi cap is this way in the anti-clockwise sense. So r cap cross phi cap will be outwards towards us, which is basically k cap along this positive z axis, right? So that is all we need in order to calculate this cross product. So I dash times dl. So dl cross b, we'll only need this term of dl. So I'll have mu naught I divided by 2 pi r into dr, and r cap cross phi cap is k cap. Okay, so the force is going to be along the z axis. So now it's very straightforward because I can just directly integrate this because the direction of force is same on the entire segment. Remember, the segment is in the xy plane only. Okay, so now I have mu naught I dash divided by 2 pi, and I have to integrate dr by r. So now all we need is the distance. What matters is the distance, r1 and r2. Once again, here you see that the curve does not matter. Whatever the shape of the segment, all we are ending up with is r1 and r2. That is the distance of 1 and 2, whatever the shape of the curve is. Okay, so this will become mu naught I dash divided by 2 pi ln of r2 by r1. Okay, and this will be in k cap direction. Alright, so this is the value of the force. So let's look at a very simple example or an application of this. So I have, let's say, an infinite line wire in this manner, then I have a current carrying segment that subtends some angle here, let's say 30 degree and let's say 60 degrees, right? And this is some distance, let's call it D. Okay, so what will be the force on this current carrying segment I dash? So we already found the force would be mu naught I dash divided by 2 pi ln of R2 by R1. So how much will R2 be? That will be D sec 60 degree divided by, and R1 would be D sec 30 degree, right? Now it's pretty straightforward. So sec 30 degree would be 2 by root 3, and sec 60 degree would be 2. So I'll basically end up with ln root 3. Okay, that's the answer in the k cap direction. All right.